Hello everyone, and welcome back. Today we're going to be continuing our exploration of real analysis and discuss what it means for a function to have an elementary primitive. Some people will also use the terminology elementary antiderivative. So firstly, what exactly do we mean by elementary? The definition given today is actually more of a historical definition, and some authors and literature and books and just some people, even students, may redefine elementary to include more or possibly even less functions mentioned here. But I'm going to stick to the classical definition of elementary functions, as a few of the mathematicians such as Liouville and Gauss and Riemann sort of worked with. And they said the following. So a function is said to be elementary if it can be represented as a finite number. So this is the first key concept. So you're not allowed to do infinite iterations of these things, but you're allowed to do sums, differences, products, quotients, and also compositions of functions of the types that are constants, power functions, radicals, including like cube roots and fourth roots, exponential functions, and logarithmic functions. The set of all of these combinations of functions is known as the set of all elementary functions. And if we say that they're functions of a variable x, we'll be denoting the class of these functions by ex. So ex is going to be the set of all functions that can be represented as these things. So let's look at a few examples of functions and ask to ourselves, are they elementary, at least from this definition? So example 1, let's look at f of x is equal to x cubed plus 5x squared minus 2x plus the square root of x. So we have a bunch of power functions, which is technically a monomial, a sum of monomials. So that obviously is an elementary function. We also have a radical here, so that's elementary. And obviously that is a finite sum of elementaries, which obviously is an elementary function. So we clearly see that f is an element of this set. Let's look at another function. Let's define g of x to be equal to sine of x. Notice that in the definition of elementary, we didn't mention any trigonometric functions or hyperbolic functions. And you're like, well, does that mean sine is not elementary? We use it in a lot of applications, and sine actually is elementary. If you remember the complex representation of this, we can write this as 1/2 of e to the ix minus e to the minus ix with an I on the bottom. So that is a finite sum, difference, and quotient, if you view 2i as a function, of elementary functions. So if that is the case, that means sine, and also similar to cosine, is an elementary function. Let's look at its counterpart. Let's look at hyperbolic cosine of x. Similarly speaking, you can represent this as 1/2 e to the x plus e to the minus x. That's obviously a finite sum of exponential functions, and hence that function is indeed elementary. Now let's make these examples a little bit more curious looking. Example 4, let's define j of x to be equal to the antiderivative of 1/1 plus x squared. So 1/1 plus x squared is a rational function, but what is its antiderivative? So we should know that the antiderivative of 1/1 plus x squared is going to be equal to c plus arc tangent of x. Now, c obviously is an elementary function, but what about arctangent? Again, I didn't mention any inverse trigonometric functions, but keep in mind, if trigonometric functions can be represented as exponential functions, then their inverses should be able to be represented in terms of logarithmic functions, and indeed they can. So for the arctangent function, you should be able to show this is equal to c minus I/2 times the natural logarithm of ix minus 1 over ix plus 1. So that's obviously a composition of a logarithm with a rational function times a constant added with another constant. That's just an elementary function. So we see that the arctangent function, any scalar multiple shifted of it, will also be an elementary function. So the antiderivative of 1 over 1 plus x squared is indeed elementary. Now, let's make this a little bit more tricky. Let's look at the integral of 1 over 1 plus x cubed. Now, this is not as easy, at least in terms of the integral, but if you know the sum of cubes identity for 1 plus x cubed, you can decompose this into a quadratic and also a linear, use partial fraction decompositions, and use some tricks with natural logs and arctans to figure it out. But you should be able to find, after some fun math, this will just be equal to negative 1/6 times the natural log of the quadratic term, x squared minus x plus 1, once you factor out into differences of cubes. And then we're going to have 1/3 times the natural log of x plus 1. That's the first linear term of the difference of cubes. And then we're going to have this square root of 3 over 3 times the arctangent of the rest of that decomposition, 2x minus 1 over the square root of 3 plus c. So we have that that's a logarithmic function, and an arctan function, and a constant. That's obviously an elementary function once you can find it. Therefore, this function k is indeed an elementary function. Let's look at a couple series, because series are actually super important. We've looked at several applications of that. Let's actually look at a series of functions ln of x, which is going to be defined as the sum from k is equal to 0 to n, so a partial sum, of negative 1 to the k of x to the 2k plus 1 all over k factorial times 2k plus 1. So is this an elementary function? Well, what do we have here? Well, we have a monomial term with a bunch of constants sort of hanging around, and it's a finite sum of monomials. Since it's a finite sum of monomials with a bunch of constants around it, we have that the sequence ln is an elementary function. Now, here's a fun question. What about its limits? So what about the limits of ln of x, right? So as n goes to infinity, so that would be the sum from k is equal to 0 to infinity of negative 1 to the power of k, x2 to the k plus 1, all over k factorial 2k plus 1. That's an infinite sum, but can it be represented as an elementary function? One can show that this is actually not an elementary function, but not because of the infinite sum. Because if you remember, e to the x is an elementary function, and that can be represented as an infinite series, because that's just x to the k over k factorial if we center it at 1, and that's obviously an elementary function. So the infinite series isn't the problem. So what actually is going on with this particular function? And are there any other functions out there that are not elementary? Let's introduce the theorem that actually helps us pave the way for this discussion. So this theorem, which is going to help us determine whether a function is elementary or not, is sometimes dedicated to Liouville, and it says the following. Suppose that we have some function I of x that is represented as the product of f of x and the exponential of g of x, with a requirement on f and g that both of them are rational functions, so quotients of polynomials. Then the antiderivative of I of x is elementary, and sometimes we will say that this object is the elementary primitive of ix if there exists another rational function h such that the antiderivative of I, i.e. the elementary primitive of I, is equal to h times the exponential of g of x plus some constant c at the end. Now, in order to find this rational function h, or to see if it even exists, this particular phrasing of the theorem is actually not quite useful. So let's actually look at this expression in a little bit more detail. So if the integral from 0 to x, and you can take any base point a, for example, and let's write this as I of t dt, and let's assume that this is equal to c plus h of x times e to the g of x. Now let's see if we can find a nice representation for finding this h if it does exist. So using the fundamental theorem of calculus, I can differentiate both sides of this equation with respect to x. Once I do so, the left-hand side is just going to turn into I of x, and that's going to be equal to, so the derivative of c is going to be equal to 0, and here I can use a product rule. So I'm going to have the first times the derivative of the second, so e to the g of x times g prime of x, and then plus the second eg of x times h prime of x. And remember, I of x is just f of x e to the g of x in disguise. So we have f e g is equal to h of x e g of x times g prime of x plus e g of x times h prime of x. Note here that we have e to the gx in every single term of this expression, and that's never equal to 0 as long as g of x is not finite, or infinite, or negatively infinite. So this is going to be equal to, f of x is equal to h of x times g prime of x plus h prime of x. So if we take this and view it, keep in mind h is the unknown variable, f and g are known. So this is just an ordinary differential equation in h, right? So we can view this in the differential equation perspective as h prime plus g prime h is equal to f, right? And that's our ODE. And keep in mind, our integral of f e g is an elementary function if there exists this h that is rational such that this differential equation is satisfied. Right? So let's look at a couple examples of functions that do not have elementary primitives and the proof of them. The first example that I want to do is actually a quotient of two very nice functions, e to the x and x. And the claim is that the antiderivative of e to the x over x doesn't exist in the set of elementary functions, right? So two nice functions, their quotient doesn't have a nice antiderivative in terms of these other functions that we've mentioned. All right. So how are we going to prove that this does not have an elementary primitive? So the first thing that I want to do is rewrite this integral in the form the integral of 1 over x times e to the power of x dx, so that I can easily identify my f and my g, so I can use this Liouville theorem directly. So my f of x, in this case, will be 1 over x, g of x will be equal to x, and keep in mind we need to find g prime of x, and in this case that's going to be equal to 1. Right? So assume that the integral of e to the x over x dx does belong in the set of rational numbers. That means we're going for a contradiction. If that is the case, that means there exists some function y that is a rational function such that y prime plus g prime of x, y, must be equal to f of x. So substituting our g prime and our f into this differential equation, we're going to have y prime plus 1 times y is equal to 1 over x. So our integrating factor will be e to the 1, e to the integral of 1 dx, which is just e to the x. So using integrating factors, we can just write this as the derivative of y times e to the x is equal to 1 over x e to the x. Right. Now I'm going to integrate both sides with respect to x once I multiply both sides by a differential of x, and I'm going to have that our solution y of x will be equal to e to the minus x times c plus the antiderivative of 1 over x e to the x dx. Right? Now, something very interesting here. Here is this little integral that we're actually trying to study, right? And keep in mind, we're assuming that this is a rational function. So either A, it's a polynomial, which means it's continuous and differentiable everywhere, or it's a rational function, which means it has a finite number of rational singularities or monomial singularities, you know, like 1 over x minus 1, where x cannot be equal to 1, so it has that little pole there, right? So those are the things that we're going to be looking for in order to construct our contradiction, right? So if it has something else, some property that rational functions don't have, that's all we need. So let's investigate this integral a little bit. So I'm going to be using, let's do integration by parts. Let us choose our u to be equal to e to the x because this derivative is actually pretty nice. And then we're going to have our dv to be equal to everything else. So dv will be equal to 1 over x dx, and its antiderivative is pretty friendly. We're going to have natural log of x. So once we have that, what are we going to have? So we're going to have y of x will be equal to e to the minus x, then we're going to have c plus uv, so e to the x ln x, minus the integral of v du. So we're going to have ln x e to the x dx. All right, so we have that. And then let's actually do one more integral. Let's do the same exact approach. Let's assume that u is equal to e to the x again. So du will be equal to e to the x dx. And then dv will be equal to the natural log of x dx. So v will be equal to x ln x minus x plus c. But we don't really need our c here because we've already have that taken care of. So using that, what we're going to have is e to the minus x, and then c plus e to the x natural log of x minus uv. So we're going to have uv, so e to the x natural log of x plus x e to the x minus the integral of v x ln x minus x e to the x dx. Now, obviously you could do this integral again. You do have to break it up into two pieces unless you have some clever method to deal with that. But keep in mind, we need to look for a contradiction as quickly as possible, else this integral is going to get really nasty. So keep in mind, this little exponential minus x is going to be distributing over here. So that's going to give us y of x is equal to c e to the minus x. Keep in mind, y is irrational. So it doesn't have that exponential decay term in it. So that's a red flag. So hopefully there's another positive e to the minus x there that has the opposite coefficient of c, right? That is, we need a minus c e to the minus x. So we should have some finite combinations that have some arbitrary constants in front of them, hopefully, right? So we can get this out. Then if we distribute that term to the next, we're just going to have natural log of x. Now that has its own bit of issues because notice x cannot even be equal to 0. That is an infinite discontinuity, but it's a logarithmic one, which rational functions don't have. So this natural log needs to cancel out with a negative natural log somewhere. Then we're going to distribute to the next one, and what are we going to have? We're going to have minus x to the natural log of x. There's another logarithmic singularity. And over here, we're actually going to have a friendly little x. So this is actually the only term that we're happy with seeing. And then we're going to have our, let's not forget that little minus sign. So minus e to the minus x times the integral of x ln x minus x e to the x dx. Now, you should be able to see that once we integrate this, we're going to have another polynomial multiplied by the natural log of x. Just like we have 1 here, we have x here. That x is going to generate into an x squared because that's what we're going to be choosing to be our dv, right? So x needs to integrate to x squared in order to differentiate back down to x, right? So that term with the natural log of x's is never going to vanish. So this function y will always contain a polynomial multiplied by a logarithmic singularity, right? And you should be able to prove that in some rigorous fashion using mathematical induction on that function, right? So once that is done, we can see that y contains a non-vanishing logarithmic singularity at x is equal to 0. So since that logarithmic singularity will never vanish, it's got a couple issues here. For example, that e to the minus x, it might go away. We would have to look at a couple more terms here in order to sort of investigate that. But that logarithmic singularity definitely is not going to go anywhere. So since that is the case, y is not rational, and that's our contradiction. So if that is the case, that means the integral of e to the x over x dx is not an elementary function. And since it is not an elementary function, since it is such a well-behaved function, this motivates the creation of a newly created special function, which I'm going to denote as capital EIx, which is the exponential integral, and one usually defines this as the integral from 0 to x of e to the t over t dt. And using the fundamental theorem of calculus, you should be able to show that the derivative of this newly defined function is just precisely equal to e to the x over x. And similar, if somebody says, oh, what's the integral of e to the x over x dx, you will usually just respond with, oh, that's just EIX plus c. And they're like, oh, why are you introducing EIX? Do you not know the answer? And you're like, yeah, that is the answer because it doesn't have an elementary representation. The next function that I want to investigate is sometimes referred to as the integral of a Gaussian, which if you've studied statistics and probability, you definitely have seen this function somewhere, especially if you discuss the normal distribution. And the claim here is that the antiderivative of a Gaussian is also non-elementary. That is, a Gaussian does not have an elementary primitive. So the first thing that we need to do, since we have an exponential form of an integrand, is identify our f and our x. So f of x in this case obviously is going to be 1, and g of x is going to be equal to its exponent, minus x squared, whose derivative in this case will be equal to minus 2x. So let's see if we can prove that this does not have an elementary primitive. And again, we're going to assume that it is. So assume it does. So we're going to go for a contradiction again. So that means there exists a function that is rational such that, again, y prime plus g prime of x, y, will be equal to g of x. And from our f, g, and g prime, we have the differential equation y prime minus 2xy is equal to 1. So, using our integrating factor, just like we have before, this is just going to turn into the derivative with respect to x of y e to the minus x squared is equal to e to the minus x squared. And then once we multiply both sides by a differential of x and then integrate, we're going to have that our solution, y of x, will be equal to e to the positive x squared times c plus the antiderivative of e to the minus x squared dx. Now, again, y is assumed to be rational, so we're looking for any signs of a contradiction. The sooner, the better. Now, there isn't any integration by parts, things that might be trivial here, but keep in mind we do have an exponential function, and the Taylor series is usually a nice place to start for that. Right? So if we look at this from the Taylor series perspective, you're going to have that this is equal to e to the x squared, and then plus c times the antiderivative of the sum from k equal to 0 to infinity of minus 1 to the k, x to the 2k, all over k factorial dx. Right? So once you integrate this with respect to x, you're going to have a 2k plus 1 and a k factorial here. Then you're going to have a series that I actually presented at the very beginning of this discussion, where I sort of claimed that this does not have an elementary primitive, or at least I had a non-alternating version of it. So once we look at this, what are we going to have? So we're going to have y of x is equal to e to the x squared times c plus the sum from k is equal to 0 to infinity of negative 1 to the power of k of x to the 2k plus 1 all over k factorial times 2k plus 1. Right? So it's very important to note this does not have any discontinuities. So it has no discontinuities in R nor the set of complex numbers. It doesn't have any x's in the bottom, right? And the same thing can be said once you expand that e to the x squared out. So if it doesn't have any singularities, especially rational singularities in R or C, that means that this is a special type of rational function. This is just a polynomial. So it is just a polynomial, which means it has finite degree. Right? Let's say if it's of degree m. Now let's see if we can build our contradiction here. So what exactly do we have? So if we expand e to the x squared in terms of its Taylor series, what are we going to have? So we're going to have y of x, not y prime of x, but y of x, is equal to c times the sum from k is equal to 0 to infinity of x to the 2k over k factorial, and then plus the sum from k is equal to 0 to infinity of minus 1 to the k, x to the 2k plus 1, all over k factorial 2k plus 1. Right? Now, I want to analyze this series for just a moment. Notice that when k is equal to 1, 3, 5, 7, 9, all the integers, this term will be negative. In particular, there are infinitely many negative terms here once I look at the odd indices. Right? Let's pretend and give this the benefit of the doubt that y is indeed a polynomial, right? If that is the case, these negative terms must cancel with these positive terms, at least infinitely many of them, right? Because keep in mind, we need a finite degree term here. But even if, in the strong case, that they do cancel, you're still going to be left with the terms k is equal to 0, 2, 4, 6, 8, and so on. Right? So if that is the case, then it's impossible for you to have a finite degree. Right? So this is not a finite degree term. And you can look at all the terms in the series and look at the coefficients and show that infinitely many of those coefficients are not going to go into 0. You'll get the same exact conclusion, but that's just sort of a observational view of how you could go about proving it in a rigorous fashion. Right? So it's not no finite degree term, which means that this is not a polynomial, which gives us our contradiction. So that means that the integral of e to the minus x squared dx is not an elementary function. And this motivates the creation of a new function. But before we do that, do recall, at least from multi-calc and polar coordinates, that the integral from 0 to infinity of e to the minus x squared dx will be equal to the square root of pi divided by 2. So that means if I multiply both sides by 2 over square root of pi, I do get 1. So if this is not a elementary primitive, we also have that the integral of 2 over the square root of pi e to the minus t squared dt also will not be an elementary primitive. So if that is the case, defining this integral, since it has, a probability value of 1 from 0 to infinity, is a little bit more useful in practice, and that's usually what the literature does. So this motivates the creation of a new function, ERF, or the error function of x, to be equal to the integral from 0 to infinity of 2 divided by the square root of pi, actually the integral from 0 to x of 2 over the square root of pi, e to the minus t squared dt. And it's obviously clear to see that ERF of infinity would be equal to the square root of pi of, ERF of infinity would be equal to 1, and ERF of 0 would be equal to 0, right? And that's a very beautiful integral, several applications in probability theory, and that's how to prove that it does not have an elementary representation. So up to this point, we've presented two functions that do not have elementary primitives, the exponential integral and the error function, and there are infinitely many force special functions out there that have so many applications in their own right, and of course we do not have the time to discuss them all, but there are some other notable functions that I definitely want to mention because they come up in a variety of places, especially in early level calculus courses. The first one is a counterpart to the error function. Instead of a minus t squared, it just changes it to a positive t squared. And we call that function the imaginary error function. And this is defined to be equal to the integral from 0 to x of 2 divided by the square root of pi e to the positive t squared dt. Another very important integral would be the sine integral, psi of x. And this is defined to be equal to the integral from 0 to x of sine of t over t dt. Proving that this does not have an elementary primitive is a very good exercise for you in case you're interested. And also the hyperbolic sine integral xi of x will be equal to the integral from 0 to x of the hyperbolic sine of t over t dt. Now the motivation of these definitions for sine t over t and hyperbolic sine t over t is from the fact that the limit as t goes to 0 of the sine of t over t is equal to 1. And the same thing can be said with hyperbolic sine over t. And L'Hopital's rule can quickly verify in case you forget that, right? So even though we're going for 0 and we have a singularity at t, it's actually a removable discontinuity, so we do not have any issues there, right? Now, Are any of these integrals connected to each other? Obviously, there are some integrals that are connected to each other. Another special function out there would be the logarithmic integral, usually denoted by lowercase li of x. And this is defined to be the integral from 0 to x of dt over the natural log of t. Obviously, when t is equal to 0, natural log of t is equal to minus infinity, but 1 over minus infinity would be equal to 0, so it sort of fixes that issue since it's on the bottom. But a nice connection and a couple of nice elementary exercises you can do is to verify that Li evaluated at ex, so composed with ex, is actually equal to the exponential integral, and also Lix is the same as the exponential integral composed with the natural log of x. So this function is very closely connected to its exponential counterpart. So the exponential integral and the logarithmic integral are sort of connected, just like the logarithm, the natural logarithm, and the natural exponential. Now, there are a couple other functions that are worth mentioning as well, and one of them is known as the polylogarithm function. Now, the polylogarithm function on the surface might not look like an integral defined function, but it is in disguise. But classically, it's usually defined as a parameter defined function, Li subscript s of x. S is a parameter, and this is going to be equal to the sum from k is equal to 1 to infinity of x to the power of k over k to the power of s. Now, a couple very important questions you might be asking, well, is this a elementary function? It's defined as an infinite series, so that's definitely a potential red flag, but maybe sometimes it is and sometimes it's not. But if you look at a couple special values, we'll actually see a couple other functions that we've discussed previously. In particular, if you look at Lis of 1, that's just going to be equal to the sum from k is equal to 1 to infinity of 1 to the power of k, well, that's just going to be equal to 1 over k to the power of s. And we know that that's the Riemann zeta function evaluated at s. And obviously, we already know that the domain of the zeta function is starting at 1 and goes up to infinity. So the question becomes, okay, well, is Lis1 a elementary function? One should be able to show that the zeta function is not an elementary function. That's a fun little exercise as well. Now, another very closely related function, as you might remember, let's look at Lis of minus 1. That's going to be equal to the sum from k is equal to 1 to infinity of minus 1 to the power of k. And let's throw a minus so we can have k plus 1 there, all over k to the power of s. And that is equal to the negative of the Dirichlet-Eta function evaluated at s, and keep in mind that the domain of the Dirichlet-Eta function would start at 0 to infinity, but not include 0. So the polylogarithm is actually very closely related to the Dirichlet-Eta and Riemann zeta function, and you can also show that the Dirichlet-Eta function is not an elementary function. So that's actually pretty interesting. Now, how can you show that the polylogarithm function is most of the time not elementary? So you would have to present this in the form of an integral. So you can use Liouville's theorem maybe. And the recursive definition for the polylogarithm actually makes this obvious. So Lis1, and this is a fun exercise, will be equal to the integral from 0 to x of 1 over t times Lis of t dt. And you should be able to figure out several different variations of the polylogarithm. I would suggest starting off by looking at what exactly is Li0 of t equal to, and then you can use this iteration to start building your polylogarithmic functions, and then analyze them term by term if you desire. Right? Now, you might be wondering, I introduced several functions here, for example, sine over t, e to the t over t, 1 over ln t, but I didn't mention any cosine things. And I want to just sort of mention why and sort of close off there. So the cosine integral ci of x can be defined similar to the sine integral as cosine of t over t dt. Now, in order for this to sort of work, you need to make these bounds very strange, in particular the integral from x to infinity with a minus sign in front, and there's a couple other variations as well. But this isn't very natural. If you remember from single variable calculus, there is a limit that we use in proving the derivative of cosine is minus sine, and that's the limit as t goes to 0 of cosine of t minus 1 over t. So it's actually more natural to define a special function in terms of this difference. And you actually can very easily by this. You can actually write this integral equivalently as the natural log of x plus the Euler-Mascheroni constant plus the integral from 0 to x of that function, the cosine of t minus 1 over t dt. And obviously this constant might seem very random, especially if you don't know about the Euler-Mascheroni constant and its applications, but you could technically take that constant to be any constant you want if the only thing you're aiming for is that the difference of the cosine integral function, which would be equal to what? So the different derivative of the cosine integral function, that would just be equal to the cosine of x over x, regardless of the definition that you take. And that's actually a fun exercise, especially for the right-hand representation. Right, but both of these are equivalent definitions. I'm more of a fan of the right-hand one, even though the left hand does sort of look a little bit more easier to remember. But if you have family, note cards and formula sheets and stuff like that, it doesn't matter. But the right one, at least to me, has more applications and intuition tied to it. And this also helps motivate the creation of the hyperbolic cosine integral function, and you can define it in a very parallel fashion as the cosine integral function as the natural log of x plus the Euler-Mascheroni constant plus the integral from 0 to x of the hyperbolic cosine of t minus 1 over t dt. And obviously the derivative of the hyperbolic cosine integral function would just be hyperbolic cosine of t x over x. Right? But again, there's so many special functions out there that are of course motivated to be defined because they are not elementary functions, and so many identities that sort of tie all of these special functions together, which we'll discuss at a much later time. Hope you enjoyed this video, and I'll see you in the next one. Take care.